Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. Good evening, Dr. Dave. How are you?
Good evening. I'm good.
All right. How is everything in the world of science?
It's generally interesting. There's a nice thing which I saw was recently, I think it was actually on Tuesday, a small asteroid hit the Earth over Sudan. It's about 5 metres across and it released a similar amount of energy as about 1,000 tonnes of dynamite going off, or TNT going off strictly. But that's actually not very unusual. This happens at least every couple of months, if not more often on Earth. But this was the first one that someone spotted before it hits the Earth.
Oh.
So they managed to get three days warning. So sometime on Sunday, they actually saw a little tiny pinprick of light moving across the sky, because they've got a load of now they've built some sort of automated telescopes which move around the place and take pictures of the sky very regularly. And if they see a spot moving, then they can work out what it is, work out where it's going. And they worked out this one was actually going to hit the Earth with 3 days warning, which possibly isn't enough to do anything with it, but it was a very small one. But it does mean that possibly in the future with bigger ones, which could be more dangerous, so things like 50 metres across, which could do really serious damage, releasing like millions of tonnes equivalent of TNT going off, we might get enough warning to be able to do something about it, or at the very least plan for the disaster which would happen if it hit somewhere nasty.
Okay, so what I'm picturing here then would be a very large truck with a big trampoline type thing, so that you could kind of and just sort of ping it back into space while you built somewhere to kind of guide it down to, or destroy it to, recycle the energy that it would bring.
I think what people are more looking at is ways of, if you can see one of these coming sort of 2 or 3 years in advance, or preferably 10 or 20 years in advance, you can send up some kind of spaceship up near it. There's various things you can do. You could either just put a big mirror and shine light on one side, so that gets a little bit of a push from the light, and because you get gases evaporating off it, they like a rocket and push it slightly off course. If you start off early enough, all you've got to do is move it in 10 years enough to miss the Earth, and you're fine.
Right, OK, fair enough then. Now, Foxy has asked if Dr. Dave believes in spontaneous combustion, and if so, how does it work?
I think what he's talking about is spontaneous human combustion, where various people, there've definitely been found some people who appear to have burnt to death with no apparent reason to set fire to them. Lots of people have suggested that this could be something supernatural, or all sorts of strange things going on. They tend to be people who are quite fat, I think would be a better way to put it. So there's lots and lots of chemical energy there. So it is quite possible there's enough energy in a person that if you can get them burning, they will keep burning. If you've got enough fat there, because fat is what you use in a candle. It's basically an energy store. So if you can release that by heat, it's not a very pleasant thought. So I think people can certainly burn if you have enough fat, or bits of people can. But whether it can start spontaneously, I'm not sure.
All right, then. I found a little something that apparently scientists have outdone nature, won't be a first time, will it, to produce a material 10 times stickier than the feet of a gecko. So, Dr. Dave, the feet of geckos, then, gecko feeties, how exactly do they work?
Yeah, geckos are a really interesting creature. They'll sort of crawl around, they'll climb walls. They'll even walk across ceilings because their feet are so sticky that they can actually stick onto things. And the way they work is basically on their feet, they've got little hairs. Mm-hmm. On the end of the hairs, these hairs split up into even smaller hairs. And those hairs split up into even smaller hairs. And the reason why that's useful is that if you get two objects incredibly close together, sort of within the radius of an atom or so, then they actually stick together. It's for the same reason that materials will stick to each other. So you get a lump of something like wax. It's all held together by a force called the van der Waals force. And this is basically when molecules are very close to each other, they stick. So if you get two things very close to each other, they will stick quite well. The reason why things don't stick normally is that the surfaces are very rough. So only a very tiny proportion of each surface is actually touching, so they don't stick very much. You get a bit of friction, but nothing huge. However, if you've got lots of little tiny hairs and hairs on hairs, then all the ends of them can actually touch the surface of the material which you're standing on. And so you get a very, very large van der Waals force, which sticks you to the object, to the wall or whatever. And so geckos can walk up walls, across ceilings. They can't stick to anything which is oily, because they can only stick to the surface. If that surface isn't very strong, then they'll fall off.
Yeah, I seem to remember staying in a cabana once, and they were walking across the ceiling on the straw. You know, with like a thatched straw roof and that type of thing, which is so a variety of surfaces then they can stick to. And I wonder if people with split ends, if they rub a balloon on their head, maybe they just get more static in their head on the balloon. Is that right?
In fact, split ends will charge off a balloon better and would transfer more charge to the balloon and keep more charge themselves, because when you charge something up, all the electrons repel each other. And so the more space they can take up, the more electrons you can get onto a hair. So if it's split, then you've got more edge of the hair, so the electrons get further apart. So you can you could charge things up better with split ends.
OK, I'm getting the hang of this science stuff. Another question here, this time by email from Rob, who's in the USA. Lovely that you're here listening to us. Now then, he says, what happens as liquid nitrogen becomes a gas?
Basically, something very similar as to when anything else becomes a gas. So if water or nitrogen boils, it starts off as a liquid. So all the particles, they're stuck to each other in fact, with liquid nitrogen, it's these van der Waals forces again. So they're attracted to each other, and they need to get quite a lot of energy to escape this attraction and fly off randomly, because in a gas the particles are flying off all around the place. In a liquid they're moving past one another, but they're still stuck to each other, so they can't actually escape. And then basically, as you heat something up, some of the particles will have enough energy to escape, and the hotter you get, the larger proportion of them that will do that. So slowly more and more of them can escape. So even if you're below the boiling point, some of them will have enough energy and they'll evaporate, which is why if you put water on a warm plate, even though it's not boiling, it will evaporate. Then eventually the pressure of this this gas which is escaping gets larger than atmospheric pressure, which means that it can push out and create bubbles and push the liquid out the way. And these bubbles then rise up to the surface and burst, and that's what we call boiling. Basically, the particles inside the liquid, the molecules inside the liquid, have enough energy to escape, and enough of them have enough energy to push out and form bubbles, and these bubbles can rise to the top, and you've got boiling.
Well, thank you very much. And Anne. Hello, Anne from Mangers Green. Dave, here's a bit of geography for you. I don't know whether you know anything about this. She says the Himalaya mountains are commonly referred to as the Himalayas, but she thinks the correct term is just Himalaya with no S. Is she right?
I've had a bit of a look into this, and yes, I think Himalaya is the closest to what the Sanskrit language, which from around there, call it. It's just kind of hard to say, so people tend to call them the Himalayas because it's easier to say, fundamentally. They're actually a very interesting mountain range, the biggest mountain range in the world, caused because India is piling northwards towards Mongolia. Basically, the whole plate is being pushed into Mongolia, and it's slowly crushing rock. And the continental plates, so the continents are basically thick, light rock, which floats on the more dense mantle underneath. So as they crush and get thicker and thicker and thicker, they start to float upwards and you get mountain ranges. And the Himalayas themselves are really impressive, and they've got the highest mountain in the world, Mount Everest. But actually, almost from a geological point of view, it's more impressive that there's the whole of Mongolia, there's a huge area of about 1,000 kilometres across, which is lifted up by a whole kilometre, which is an immense amount of rock which has been crushed. And they actually have probably changed the climate of the whole world, because as they started to be created several tens of million years ago, I think sort of 30 million years ago or so, actually we started having ice ages, because people think that they've deflected the way the air travels around the world and could have altered the whole climate of the world and kept it a lot cooler. So, yes, the world would be a very different place without them.
Interesting stuff, Dr. Dave. Now then, Bob from Essex asks, if light speed is so phenomenally fast, how come we can measure it to the nearest millimetre? Ooh, good one, Bob, thank you.
Basically, because measuring devices we can measure time to the nearest, virtually picosecond, if not better. Naught with sort of 14, I think it's femtoseconds, and naught with 14 zeros, with a 1 after it. So if you can measure time in very, very small units, then you can measure the speed of light very, very accurately. And so you can measure distances using light, even down to millimetres.
Good stuff. How do you manage to... No, I won't go into that, Stu.
Well, I mean, basically the way you do it is you get something which vibrates incredibly quickly. So if you can get something which vibrates billions and billions and billions and billions of times every second, and you can count those vibrations, you can measure very small amounts of time.
Thank you, Dr. Dave. Right, the next one we got here is from Amy. She says that every Sunday evening her dad has a gin and tonic with lemon, and her mum has a rum and coke with a piece of lime. I can just picture that. It's just sitting there lovely.
Sounds very civilised.
But she says, why does a slice of lemon float and lime sink? That's very true if you try and squash it into the top of a beer bottle. Not that I do that kind of thing.
No, of course not.
Well, what do you reckon, Dr. Dave?
I think it's to do with the pith, because around the fruit, in a citrus fruit, you get that sort of white, pithy bit around the outside to protect the fruit and stop it getting damaged, when it falls off the tree, so it doesn't go rotten. So animals eat it, not bacteria, which won't transport the seeds around. And I think if you look at a lemon, the pith is much, much thicker than in a lime. And because pith it's quite light, there's quite a lot of air in it, so that's going to act as flotation. So if you have a lot more pith, it's basically like having a life jacket around the lemon. So although the actual lemon inside is probably denser than water because there's lots of sugar in it, the pith on the outside basically acts like a life jacket and causes it to float.
Fascinating stuff. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Right, another one here, and this keeps us on the sort of food layer, if you like, or kitchen science, because you're good at that, aren't you? Ian has said, why does toast always land butter side down when dropped? I think you've done an experiment in this, haven't you?
Yes, in kitchen science we did this very experiment. Basically, if you just get a piece of toast, it doesn't even have to be buttered, if you just mark the top of it and then push it off something about the same height as a table, about the same sort of speed as you would tend to knock something off a table. As the piece of toast falls off the table, it starts to rotate because more than half of it's over the side, so it starts to rotate. And basically the speed that it starts to rotate and how far it's got to fall means that normally it ends upside down. You can actually stop it landing butter side down if you knock it off the table incredibly quickly. And it's not sitting half on the table for long enough to start speeding up and spinning, so it doesn't actually fall over. It can land the right way up. If you knock it off incredibly slowly, you can actually get it so it will do a whole turn as it falls down. So if you very, very gently knock it off the table, it will actually be spinning so fast that as it falls down, it will end up landing the right way up. Or if you knock a piece of toast off something about 3 metres up, as I experimented in this very studio, you can get the toast to land the right way up.
In the name of science. We've got John, who sent us a text in. John says, Dr. Dave, I'm confused by the suggestion that global warming will decimate our wildlife. Would it not just be a movement northwards in our hemisphere?
Obviously, it will definitely cause problems to anything which is any creatures which only survive in the furthest north. So creatures like polar bears have got nowhere to go. So it's definitely going to be a problem for the Arctic wildlife. It could also be a problem for all the other wildlife in the world, even though if there were no humans there, it would be a bit of a pain for them. A lot of them would die, but probably they would survive because they would just move. The problem is that we're sitting on where they want to move to. So at the moment, you've got little islands of places where the wildlife can live, with lots of human habitation in between, where they just can't live. We'll probably either kill them or there's no food for them. And so even though the climatic region where they want to live will probably move northwards slowly, if they've got no way of getting to that new place because there's a load of farms or cities in between, then they can't get there. So they've got no choice but to die out, basically. It wouldn't be that much of a problem if humans weren't there, but because we use so much of the planet, it can cause big problems.
Now then, we've got some more questions here, this time one by email, and this is quite complicated actually. It's from Race. He says, do solar flares disable microprocessors and circuitry like an electromagnetic pulse would?
Solar flare is basically a big explosion on the sun which fires out lots of very high energy charged particles, so either electrons or protons or possibly even bits of helium and things, whatever's in the atmosphere of the sun, fires those out incredibly fast at the Earth. If you're on a satellite orbiting the Earth, then this can be very dangerous because it's basically very, very heavy radiation. Mm-hmm. And this can damage microprocessors in satellites in a different way to an electromagnetic pulse, because basically this is dumping energy into the microprocessor itself. These particles will go straight through. If one of them stops, then you can actually build up large voltages inside the circuitry of the microprocessor. Well, you can get large voltages and then get sparking inside the processor. Or you can basically, these particles can actually just rearrange the atoms inside the processor and stop them behaving the way they should do. So they stop being a transistor, so it stops working properly. That's only really a major problem in space. The bigger problems on Earth are the fact that these are huge electric currents and they're changing very fast. And large electric currents make magnetic fields, and changing magnetic fields make electric fields. And so you can drive big electric currents around power grids. Power grids are designed for alternating currents, which just goes one way and then back the other way and one way and back the other way. And they work well for that. But if you've got a big loop of power grid, like they have in Canada, during these solar storms, you can actually get huge direct current electric currents going around these loops. And these can heat things up because the system's not designed for it at all, and just basically overheat things, melt things. Transformers melt and break, and it knocked out the whole of Canada's power, or large portions of Canada's power, a few years back, probably like 5 or 6 years ago. Basically due to this induction, it's called electromagnetic induction, this big induction effect.
Now then, Dr. Dave, Steve in Peterborough asks, if man continues to drive so many cars around the world, even using biofuel, how will we ever reduce global warming?
Yes, the more energy we use, then the harder it's going to be to cut down enough in order to stop heating up the world and releasing too much carbon dioxide. There are ways around it. They're going to cost a lot of money to generate the power to power cars not using oil, because oil is such a wonderfully cheap source of power. But fundamentally, oil is going to run out anyway, so it's just a case of doing that slightly earlier than we would do anyway. There are ways around it. The amount of energy hitting us from the sun is something like 10,000 or 100,000 times more than our civilization needs. So fundamentally, if we can work out some way of making good, cheap solar panels which are efficient, then we don't have to cover that much desert in order to be able to generate all the energy we need for transport and everything. Then you've got to develop good batteries or some other way of storing energy. But that's possible in the next 50 or 100 years. It's just whether we've caused so many problems with the planet by then that we're in trouble anyway.
So you think we'll ever be able to have a solar-powered car then?
Probably not solar power on the car itself, because the amount of energy hitting the car is very small compared to the amount of energy that the car uses. But possibly a whole of the solar panels on your roof, which would then charge up your car. So it would charge up a battery, which would then charge up the car or something like that. It's certainly possible.
Robert in Colchester has called in to say, is it true that it snowed on Mars this last week or so?
Probably not by your definition of snow, because what you normally mean by snow is snow landing on the ground and forming nice little drifts you to run around in and play. But they have detected snow in the Martian atmosphere, very high up, sort of 2 or 3 kilometres up. They had a laser and they were firing the laser into the atmosphere and watching what bounced back. And what bounced back was indicative of there being snow up there. So, yes, there was snow on Mars, but as far as we know, it hasn't touched the ground yet, although it's not to say that it won't do in the future.
Interesting stuff. Now then, Nigel says, if we are observing light from mind-blowing distances, I presume that all energy comes from burning suns. Presuming that they fade and die, has anyone estimated the proportion of those we see that no longer exist? Going on from that thought, has planet or sun creation slowed down, and how would we know? Nigel in Willen Park.
I don't know whether star creation has slowed down. It's definitely slowed down in our part of the galaxy. No stars are. It almost certainly has slowed down. Yes, most of the energy we see is coming from sun stars, and they do slowly burn out. I think the sun has got at least another 5 billion years. Basically, I think it's been living for it's been running for about 5 billion years now. The universe is about 13 or 14 billion years old. The sun's got another 5 billion years before it will puff up into a red giant and possibly is out to the orbit of at least Venus, if not Earth. And then it will probably live a few more billion years after that, and so you shrink and shrink and shrink. I would have thought that there was more star creation earlier in the universe just because there was more hydrogen gas floating around because it hasn't all accumulated into stars yet. We can tell, I could imagine that we could tell, I don't personally know, that because if you look, the further away you look, the light takes a long time to get here, so you can actually essentially look into the past. So if you look at a galaxy billions of light years away, then you're essentially looking billions of years into the past. And if you look at a galaxy and see how much new star formation there is there, and then look at one closer and closer and closer and closer, you can then see how star creation has changed over time. So I'm afraid I don't know the answer, but I'm sure that somebody else does.
One last one coming up here, Dave. Why do magnets attract unmagnetized pieces of iron? Because they do some. They do.
Yeah, they do. Not all iron, not all steels anyway, because a lot of stainless steels aren't magnetic. The atoms in iron, each are little tiny magnets. Basically, they've got more electrons orbiting in one direction than the other direction, and that's basically a circular electric current. And if you make an electric current go around in circles, you may have done this at school, getting a wire and wrapping it round and round and round a nail, putting an electric current through it.
Oh, all the time.
When you put electric current through it, it turns into a magnet and will pick up small things, small bits of steel like paper clips. So inside all these iron atoms, you've basically got little electromagnets, so the iron atoms are all magnetic. And iron atoms are peculiar in that they like all lining up when they're near each other. So you get whole areas called domains, all with all the iron atoms all lined up. So you create sort of small magnets. But normally in a piece of iron, these domains are all pointing in random directions. And so, in general, a north pole from one will join up into a south pole of another domain. They form little circles, and so overall they're not magnetised, and very little magnetic field gets out. But if you put a magnet near them, they tend to line up with that magnet. So the south poles from each domain twist round. So as domains with the south poles towards the north pole of the magnet tend to get bigger and bigger and bigger, and the ones which are pointing in the wrong direction get smaller and smaller and smaller. So the piece of iron turns into a magnet itself, and it will stick to the magnet. When you take it away, it decays back to normal.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.